Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to like and subscribe, and help us out on Patreon if you can. We appreciate you. Today we are first going to define different paths to success in space. Then we will apply the rules of science and engineering to the current Starship design, and to the more powerful Raptor 2 rocket engine. We take the time to create these lessons to help you find the future that best fits you in the space industry, which will have a tremendous need for trained personnel to build and crew the spaceships and habitats that are coming. To prepare you for this new world, you will need to start deciding what role you want to play. Everything will be needed in space eventually, from rocket scientists to cooks and hairdressers. But for now, while access to space is so limited, you will need to be somewhat of a jack of all trades. But where should you start if you want to build and someday perhaps fly spaceships, and eventually live on an off-world colony? First, there is the technician. A technician is trained to accomplish a complex task. For rockets, this could be the people who assemble the rocket engines. Right now, in McGregor, Texas, SpaceX is hiring for this job. Here you will not be designing the rocket engine. You don't even have to understand how it all works. You will just have to take your place in the assembly line and attach your designated component quickly and accurately. You will need to be able to recognize when something is wrong with either your component or the assembly you're working on. And other than that, you probably have no responsibilities. This can be a regular job, and when your grandkids ask you what you did before you retired, you can say, "I made Starship engines." Technicians will be in great demand on any large spaceship or off-world colony. And when I say large, I'm referring to what will be possible when we start building our spaceships on the moon. I want you to wrap your head around something. This is the Empire State Building. This structure has a mass of 331 million kilograms. That gives it a weight of a little more than 3,247 meganewtons. To lift this thing off the Earth, with a thrust-to-weight ratio of only 1.1, would take about 1,500 Raptor engines. But to lift the same structure off the moon would require only 245 of them. Someday, humans will travel the solar system on ships this size. To make that happen, we will need the next level of space systems understanding. Engineers. To put it simply, engineers build engines. That's where the name came from. The Greeks called someone who knew how to make machines a mechanopoios or mechanikos. Today, engineers build other things also. We now use the term mechanic for those who repair existing machines, and reserve the term engineer, more commonly, for those who are both builders and creators. Aerospace engineers will be desperately needed in the space industry. Even if you don't need to become an engineer, you will need to know and respect their skills to get your project off the ground, literally. The first step to do this is to take a basic online course through an organization like edX or Coursera. These courses can be taken without charge and will give you access to some of the world's best teachers. You can take enough of these courses to know what you're talking about. The next step could be a certificate in aerospace engineering, to certify that you know the fundamentals. Then, if you need more, an associate's or 2-year degree. Now you are technically an aerospace engineer. You can probably get hired somewhere designing and building space systems. A bachelor's or 4-year degree would give you a broader knowledge base and probably more opportunity, though some of the best rocket scientists have been self-taught. We've talked about Tsiolkovsky many times, and I plan to cover Jack Parsons soon. But suffice it to say that the maximum amount of education you need is the minimum required to let you do what you want. You can go on to get a master's degree or even a PhD, becoming a doctor of aerospace science. Or take your certificate and start working in McGregor, Texas, and build your career. There are other paths in engineering. You can study space science, which focuses more on a general understanding of all aspects of spaceflight, rather than a focus on building and testing aerospace equipment and vehicles. This is what my master's degree is in, which is why the engineering nerds are always picking on me. When they design and build these systems, they will know them better than anyone else. I enjoy building things also. I've made my own magnetoplasma dynamic thruster, and that actually worked for a little while, until I shorted it out. At some point, either through the academy or company, I want to build something big. Until then, we'll evaluate existing systems, so we'll know what we are doing when we build our own. Let's apply a little aerospace science to the current Starship, and then to the Raptor 2. The Starship is planned to be a 2-stage rocket system. Both stages are made of stainless steel. And this system will use liquid methane fuel and liquid oxygen oxidizer for propellant. From numbers released by SpaceX, the booster will have a dry mass of 180 metric tons and be able to hold 3,400 tons of propellant. That gives it a total mass of 3,580 metric tons. The second stage, usually just called Starship, will have a dry mass of 120 tons and will hold 1,200 tons of propellant. That brings its combined mass to 1,320 tons. If we add 100 tons of payload, this all adds up to 5,000 tons. Now let's look at the Raptor 2 engine. Rocket engines can be optimized for sea level operation or for vacuum operation. The main difference in these is the nozzle. Unlike aerospike engines, which are my personal favorite, Bell nozzles are only ever optimized for one specific air density. To understand why that is, let's look at this diagram and consider the pressure throughout this engine. The pressure in the turbopumps must be higher than the pressure in the combustion chamber. Let's call the pressure in the turbopump P0. From the numbers I've seen for the Raptor, P0 for the methane turbopump is 512 bar. The partially combusted fuel comes through this feed pipe at 321 bar. The partially combusted oxygen is in here at 377 bar, higher than the methane coming in. So it pushes both of them into the combustion chamber, where they expand and drop down to 300 bar. Now the Raptor 1 ran up to 270 bar, producing 185 tons of force. Then the pressure was increased to 300 bar, producing 200 tons of force. This was the highest pressure of any rocket engine in history until the Raptor 2, which can operate at 330 bar, producing 230 tons of thrust. If this pressure goes to 330 here, the pressure here and here will need to increase also. Otherwise, the combustion gas would back into the methane pump, causing what scientists refer to as a bad day. The combustion chamber is low speed, high pressure, subsonic in fact. The fuel and oxidizer combust in the chamber, generating heat and products of combustion. We'll call the pressure in here PC, 330 bar for the Raptor 2. We like to imagine that this process is perfect, and in an engine like the Merlin or the RD-180, kerosene plus oxygen equals carbon dioxide and water. But the truth is much more complicated. Kerosene can create a huge number of combustion products, and this mixture will skew toward one set of product or another depending on multiple factors, not the least of which is the pressure. And this complicates calculating the engine's performance, which is why space scientists need space engineers to build and test their designs. In this process, the engineers often see improvements and adjustments that the scientists didn't know about. The more engines you build and test, the better they can eventually be. A big deal was made out of SpaceX blowing up a couple Raptor 2s not long ago. Testing something to its failure point is how you find its weaknesses. These weaknesses can then be improved or compensated for. Those engines were ran at 107% of calculated maximum power. They were supposed to blow up. If they blow up exactly when you expect them to, it's a success. There were many reasons for SpaceX to switch to methane, but the main one was reusability. Methane burns a lot cleaner and simpler than kerosene. Going through the throat of the rocket engine, the combusted gas reaches Mach 1. Again, this is not an absolute speed. This number varies with the gas mixture and temperature. The pressure in here is usually denoted as PT. The area of the throat as AT, but is often shown as A star. The gas then expands into the nozzle, becoming supersonic. High speed equals low pressure. This is Bernoulli's principle. and the pressure continues to drop as it speeds up along the length of the nozzle and comes out here. The pressure when it reaches the end of the nozzle is the exhaust pressure, which we call PE, and the pressure outside, PA. PA is the ambient pressure, 101,325 pascals at sea level, but we usually simplify this to 1 bar, 100,000 pascals. In a vacuum, this number is essentially 0. The perfect nozzle reaches the exact outside pressure just as the exhaust gas exits. This would give you the maximum possible exhaust velocity, or VE, and the maximum possible efficiency. When you watch a rocket engine firing, like the SpaceX Raptor or the BE-4, look at the exhaust plume. When it flares up like this, the nozzle is underexpanded. This means the pressure of the exhaust plume is still higher than the pressure outside. This engine is optimized for a higher altitude than where it's being tested. If the exhaust plume was pinched down and actually even extending into the nozzle would be overexpanded, and instabilities like this could cause oscillations that would tear the engine apart. Once the rocket reaches space, a vacuum, it is impossible to fully optimize the nozzle. You would need an infinite nozzle for the exhaust pressure to drop to 0. What we do instead is balance the mass of the nozzle with the benefit to efficiency. That is why nozzle ratio is important. When we search online for statistics, there are multiple sources. Number 1, and given the most weight, is something published by SpaceX. Number 2 is anything said directly by Elon or one of the other SpaceX developers in an interview or on Twitter, with the understanding that either of these can rapidly change at any time. Number 3, and far behind the other two, are what educated sources say on media platforms. My searches have found several different nozzle expansion ratios from some seemingly knowledgeable sources. How can we evaluate these? Let's start at the beginning. I've seen numbers for the Sea Level Raptor stating the nozzle expansion ratio is anywhere from 34 to 40. 40 is from this table. There will be a link in the description. Let's start there and examine that value with some equations. The expansion ratio is usually denoted with this symbol. This is a lowercase or lunate epsilon, and we will set it at 40. The Vacuum Raptor is currently listed by some sources as 80. But rapid prototyping and iteration means everything is in flux. We'll get to that one later. If we start here, it would mean that the area at the end of the nozzle would be 40 times the area of the throat. Let's look at the area at the end of this nozzle. SpaceX has said that the diameter of the Sea Level Raptor nozzle exit is 1.3 meters, about 52 inches, a little more than 4 feet. The area of a circle is calculated by the equation A equals pi r squared. A diameter of 1.3 meters would be a radius of 0.65 meters. If we square that, we get 0.4225, multiply that by pi, and we get 1.33 square meters. Now we have the area of our nozzle exit. This is usually denoted AE, and we can calculate the area of the throat. We do this by setting the expansion ratio to 40, assuming it's correct. Then we can divide 1.33 square meters by 40 and get 0.0332 square meters. This should be the area of the throat of the rocket engine, A star or AT. We then rearrange our equation to solve for radius. If A equals pi r squared, then A over pi equals r squared, and r equals the square root of A over pi. So 0.0332 divided by pi is around 0.106 square meters, and the square root of that is about 0.103 meters. So the radius of the throat should be about 10.3 centimeters, making it 20.6 centimeters or about 8.11 inches across, if the numbers we could find are correct. The purpose of these exercises is not to know exactly what SpaceX has done, but to be able to calculate these values for ourselves. As far as I can find, the Raptor 1 Sea Level and vacuum versions had the same throat area. The vacuum versions of rocket engines usually differ from sea level by the size of the nozzle, though the oxidizer to propellant ratio might be adjusted in some engines also. For a vacuum engine, the exit of the nozzle should be much bigger. If it is 80 times the area of the throat, as some sources say, then 80 times 0.0332 square meters equals a little more than 2.65 square meters. If we want to get the diameter of the nozzle exit for a double check, we divide by pi, getting 0.845. The square root of this is 0.919, and this should be our radius. Double this and we get 1.84 meters. This seems a little small to me when we look at this picture. If the expansion ratio were 100 instead of 80, we would get about 2 meters, still coming up short. If we measure the diameter of this rocket's nozzle exhaust, knowing that this one is 1.3 meters, we are closer to 2.3 meters. Running our equations backwards tells us that if the nozzle exit diameter is 2.3 meters, the radius is 1.15, squared is 1.32, and times pi gives us an area of 4.15 square meters. Divide that by our calculated throat area, and we get 125. So if the expansion ratio of the Sea Level Raptor is 40, and knowing that the diameter of the exit nozzle is 1.3 meters, we get a throat area of 0.0332 square meters. And if this is accurate, and the diameter of the Vacuum Raptor nozzle exit is 2.3 meters, with no change in throat size, then epsilon, or nozzle expansion ratio, for the Vacuum Raptor is 125. SpaceX has said it has a goal of 150, so that may be closer to correct. What else can we find? Let's look at the Raptor 2 and compare it to the Raptor 1 to try to calculate the difference in throat diameter. Here's what we know. The first Raptor 1s had a thrust of about 185 tons in Elon speak, which is a little more than 1.8 meganewtons. And it had a chamber pressure of about 270 bar, which is 27 million newtons. Now that we know the thrust, chamber pressure, and throat area, we can calculate a new number. This is called the coefficient of thrust. It is a measure of a rocket engine's overall performance. CF equals thrust over chamber pressure and throat area. Calculating the CF for the Raptor 1 gives us a CF of 2.03. Now let's look at the Raptor 2. If SpaceX did not sacrifice overall efficiency to the higher thrust, and the CF for Raptor 2 is still 2.03, we can work backwards to find the new throat area. The Raptor 2 can produce 230 tons, or 2,256,300 newtons of thrust. It has a chamber pressure of 330 bar, which is 33 million newtons. If we rearrange our equation, starting with CF equals T over P times AT, we see that throat area equals the thrust over the chamber pressure times the throat area. Solving this equation gives us a throat area of 0.0338, which, solving for radius, gives us 0.104. That's 10.4 centimeters in radius, so about 20.8 in diameter, or 8.16 inches. So from our calculations, the throat of the Raptor 2 was expanded from a diameter of 20.6 centimeters, 8.09 inches, to a diameter of about 20.8 centimeters, which is 8.19 inches. This doesn't seem like much. The Raptor 2 throat would be about 2% larger than the Raptor 1. But what if they did sacrifice some efficiency to widen the throat further and get more power? And why might they do this? The first stage of a rocket system, unless you use a gun like Gerald Bull or a drone balloon like Space Ride, is pushing the entire weight of the rocket system towards space. As long as the ship is in the atmosphere, it's fighting drag. The main components of which are skin drag, determined by surface area, and frame drag, determined by the area of the ship presented to the airflow. Think of this versus this. The sooner we get out of the atmosphere, the sooner we get rid of drag. But the faster we go while in the atmosphere, the more drag we produce. And we have to worry about dynamic pressure. We don't want to push the rocket through the air so fast that we collapse the nose. The density of the atmosphere rapidly drops with altitude, so the higher we get, the more efficient our rocket becomes. Next, we must consider that we are fighting the pull of gravity. That means our ship is constantly suffering from what we call gravity drag. Until our horizontal velocity achieves free fall, then we can stay in orbit without expending more fuel. So a low thrust-to-weight ratio would leave us suffering from a lot of gravity drag. By widening the throat, we can increase the thrust, as we get a larger mass flux of flow through the engine. This would get us out of gravity drag sooner. But this would drop the pressure in the chamber, reducing efficiency and increasing residence time. To compensate for this, we need a higher chamber pressure. And I'll say it again, the greatest innovation of the SpaceX Raptor engine is the extreme pressure in the combustion chamber. By increasing the pressure in the Raptor 2 from 300 to 330 bar, SpaceX is getting a thrust of 230 tons today. and expect it to get up to 250 soon, while maintaining high efficiency. I made a video predicting 250, and I'm happy to see it happen. I hereby predict Raptor 3 will be over 300 tons of thrust, at least, and I hope it's an aerospike. So we want the booster to get our second stage above the atmosphere as fast as possible, without generating too much drag and dynamic pressure. And we want to get it pointed horizontal as fast as possible, without it falling back to the Earth. All of these conflicting factors must be balanced to find an optimal solution. This is the job of the first stage booster. If the benefit from reducing gravity drag outweighs the reduced engine efficiency, then the loss might be worth it. This again is the Starship system, the booster, which launches at sea level, and the Starship itself, which will launch itself from the booster, at an altitude of at least 25 kilometers like the Saturn V, and perhaps up to over 50 kilometers like the Falcon 9. Let's do some math. The booster will eventually have 33 engines. If we were using the old Raptor 1 engines, each would give us 185 tons of thrust, producing a total of 6,105 tons. We know the entire Starship system has a mass of 5,000 tons. If it has 100 tons of payload, that would give us a thrust-to-weight ratio of 1.22. Now if we switch to Raptor 2s at 230 tons of thrust each, we get a total thrust of 7,590 tons. That gives us a thrust-to-weight ratio of 1.52. That's 24% higher. We can get out of gravity drag a lot faster now. Or we could go back to a lower thrust-to-weight ratio and carry some more mass, though we have to remember that if efficiency drops, so does our delta V. This may be why SpaceX is saying that 150 to 200 tons to orbit may soon be possible. But what about the second stage, the Starship itself? Should we also change the original Raptor 1 vacuum for a Raptor 2? Usually on the second stage, efficiency is more important than thrust, as long as thrust is adequate. SpaceX has spoken about adding 3 more vacuum Raptors, to have a total of 6 vacuum Raptors. These would not gimbal, only the 3 sea-level Raptors in the center would. It would be possible to use thrust vectoring to control the Starship, or we could use hot gas thrusters to keep the nose of the ship pointed in the right direction. At separation, the mass of the Starship second stage will be 1,420 tons with payload. If each of the vacuum engines are optimized for efficiency, producing a thrust of 185 tons each, that would give us a total thrust of 1,110 tons. That's not enough to lift it against gravity. They could increase the pressure and get the vacuum Raptors up to 200 tons each, bringing us up to 1,200 tons. And we could fire the 3 center engines also. They would be less efficient in space, but would add thrust. With them firing at 230 tons each, we could get another 690 tons. This gives us a thrust-to-weight ratio of 1.33. Making a Starship escape abort system using its own engines a distinct possibility. Now remember, as you get closer to orbital velocity, the thrust-to-weight ratio becomes much less important than efficiency. And SpaceX will be calculating these factors to determine an optimal flight path. They seem to think that the added mass of the 3 extra vacuum Raptors is worth it. How do they make all these calculations when no booster has launched and no Starship has gone above 10 kilometers? With virtual modeling and simulation. I'm going to stop here and give our brains a rest while we watch the creation of former astronaut Gregory Chemetoff, now a professor of aerospace engineering at the Austin campus of Texas A&M University. Professor Chemetoff is creating something the world desperately needs, a real-world virtual space program, where students from all over the world can build and fly their rockets, perfecting them over time, until, by the time they have the funding to build a real one, it is as close to perfect as we can get. I'll do a full lesson on virtual modeling and simulation of spaceflight systems soon, and fill you in on other things that Professor Chemetoff is developing. Until then, take out a good spreadsheet and work through these a few times, and stay safe. Ad Astra Pro Terra.
What is Spacecraft? Spacecraft, or the Space Collaborative Real-Time Analysis and Flight Toolkit, is a platform designed to allow anyone to participate in collaborative space system and mission design. Specifically tailored to space environments, spacecraft allows for simulations to be built using user-set parameters for virtually any situation. With high-fidelity, mathematically accurate models of real physical systems, we provide the tools for engineers to design and test their ideas, as well as share them with other engineers. In industry, it is often difficult to have engineering teams collaborate on a single system. The use of different software platforms often requires that work be redone or simplified. Spacecraft avoids these pitfalls by providing all the necessary tools in one package, including industry-standard ones like NASA SPICE ephemeride data and APIs for Trick, MATLAB, and other programming languages. Spacecraft is also capable of human-in-the-loop simulation and mission design. Currently, astronauts don't get to train for a mission until a physical mock-up of their environment is built, which can take years. Spacecraft allows a mock-up to be built and iterated on in a virtual environment, which an astronaut can explore on their very first day. This means the design can receive instant feedback from the end users, which results in significant savings in development time and cost. While spacecraft can be used to simulate current missions, it is limited only by the user's own ingenuity. With spacecraft, a mission to a distant solar system, for example, can be designed by one group of users and then immediately shared with another that takes on the roles of an intrepid interstellar crew. In order to set up a mission, a user can design their own solar system using a set of star and exoplanet parameters in the Solar System Builder tool. This tool can also be used to model real exoplanets by setting some parameters, like mass and density, to their known values, and adjusting the rest as desired in order to see what a planet several hundred light years away might look like. After the environment is built, other users can design a Modular Space Transport Vehicle, or MSTV, using a set of parts that model both current and futuristic technologies. The goal here is to design a spacecraft that can provide years' worth of water, food, oxygen, and power for the crew over the course of their entire mission. Since interplanetary journeys can take months, the crew can guide their vehicle from planet to planet with an intuitive user interface that rapidly simulates the astrodynamics of their craft. Once in orbit around their target planet, the crew can scan the planet for resources and select a landing site if they decide the planet is worth exploring further. A user can then pilot a descent vehicle down to the surface of the planet as their crew watches in real time from the passenger seats. On the surface of the exoplanet, the crew can then design a Modular Planetary Surface Habitat, or MPSH, to house them as they explore the planet in search of resources like water or geothermal energy in the hopes of finding enough of them to sustain their habitat for years to come. Mission design scenarios like these can also be used as educational competitions for middle or high school students, encouraging interactive science and engineering education in a way that benefits both students and educators. Overall, Spacecraft hopes to spur creativity and innovation by providing a simple way to test, build, and create models for current and future space missions. Thank you for watching, and we hope to see you starside.